Welcome. In this video, we begin Chapter 2, Sequences and Series. We begin with a motivating section, 2.1, Rearrangements of Infinite Series. It's kind of cool. It shows some crazy things that can happen and motivates the rest of the chapter. And then we begin in earnest with 2.2, The Limit of a Sequence. The big idea is convergence. If we can really understand convergence, then, well, that's what much of real analysis is all about. 2.1, Rearrangements of Infinite Series. So a series is when you add together things, and an infinite series, well, you add together infinitely many things, and weird things can happen. Take a look at this example. I have the infinite sum, n goes from 1 to infinity, negative 1 to the n plus 1 over n. When n is 1, then my solution is just 1. When n is 2, this becomes minus a half. When n is 3, plus a third, and then minus a fourth, plus a fifth, minus a sixth, and so on. Now, if you add this series left to right, you get a number that's about 0.69. But something funny happens. Let's imagine you take half s. All right, so I just halve all the terms of the sequence. So 1 becomes 1/2. The minus 1/2 turns into a negative 1/4. The plus a third is plus a sixth. The minus a fourth is minus an eighth, and so on. So I can take half of that sum. And then we will add s to it. Take our original sum. So the thing that I had originally, 1 minus a half plus a third minus a fourth. And let's add these together. So I'm just adding straight down, and I end up, well, of course, half s plus s equals 3/2 s. So I end up with something bigger. And so adding straight down, 1 plus a third, minus a half, plus a fifth, the sixths cancel out, plus a seventh, and so on. And do you notice something weird about this 3/2 s? It is the original terms in a different order. That is crazy. This 3/2 s has exactly the same terms as my original summation, but just in a different order. And so, rearranging terms produces a value 3/2 as big. That's crazy. Here's the lesson. Addition in the infinite setting is not commutative. We have to let go of our intuition. We want what we know to be true about finite sums to also be true about infinite sums, but it's just not so. We have to lose our intuition and be really careful. Here's another example. The summation n goes from 0 to infinity of the powers of negative 1/2. So 1 minus a half plus a fourth minus an eighth plus a 16th, and so on. It turns out that in this case, every rearrangement yields the same sum, 2/3. No matter how I flip these terms around, the sum will always be 2/3. So what's going on? Infinite addition is commutative in some instances, but not others. So part of what we'll do is try to answer the question, what's the difference? How do I know if an infinite sum depends on the order of its terms? How about the associativity of sums? Let's take this simple infinite series, negative 1 plus 1, negative 1 plus 1, negative 1 plus 1, forever and ever and ever. If I pair together the terms, starting with the first two terms, well, let's see here, negative 1 plus 1, 0, 0, 0, 0. It really looks like the summation of this series is 0. On the other hand, what if we pair together the terms starting with the second term? So I have negative 1 plus 0 plus 0 plus 0 plus 0 forever and ever. It really looks like that sum is negative 1. So infinite addition is not associative. These weird things that go against our intuition, sometimes these are called pathologies. It is the pathologies that give rise to the need for rigor. Another statement in our book reads, "It may seem that progress is slow at first, but that is because we do not want to fall into the trap of letting the biases of our intuition corrupt our arguments. Rigorous proofs are meant to be a check on intuition, and in the end, we will see that they vastly improve our mental picture of the mathematical infinite." All right, so with that introduction, we are motivated to take a look at the rest of Chapter 2. We begin with sequences. So a sequence is an ordered list of numbers, and I use parentheses to indicate a sequence. So be really careful here, it makes a difference. I use braces to indicate a set, and I use parentheses to indicate a sequence. In sets, there are no repeats and order doesn't matter. In a sequence, numbers can repeat and order does matter. So here's an example of a sequence: 2, 4, 6, 8, forever and ever and ever. Here's another one: half, 2/3, 3/4, 5/6, on and on and on. So the first two sequences are given by explicitly listing the terms. I can give a formula for the terms of the sequence, kind of like a summation formula where I have a subscript and a superscript. N goes from 0 to infinity of 1 over 2n, so this turns into the sequence 1 over 1, well, just 1, followed by 1/2, followed by a 4th, followed by an 8th, and so on. Or I can indicate the sequence by putting just a sub n in parentheses, and then giving a formula for what that nth term looks like. So what is this sequence? Let's see, it starts with 1, so for all n in my natural numbers. So when n is 1, I get 2, and then after that 4, 8, 16, 32, and so on. The sequence on top diverges. It just goes to infinity, gets larger and larger and larger without bound. That second example is an example of a sequence that converges. The terms of the sequence look like they get closer and closer and closer to 1. Here's the official definition of a sequence. A sequence is a function whose domain is n. And that's kind of weird. Like, I look at this thing like, that guy, that's a function? And it kind of is. It shows us exactly how the function works. It's a function that takes 1 to 1/2. It's the function that takes 2 to 2/3. It takes 3 to 3/4, and so on. We don't actually use this definition of the sequence very often. Our intuitive understanding of the sequence will suffice. Let's talk about convergence. This is the most important definition in the course. I hope I made my point clear. You should memorize this definition as soon as you can. Here's the idea. I'll lead up to the definition in a second. I have a sequence of numbers, a1, a2, a3, and so on, and I also have some particular number, a. And I want to indicate somehow that the sequence converges to the number a. The idea is that I might set a certain barrier around a. Maybe let's call this an epsilon gate. I take some values that are epsilon away from a. So epsilon, I usually think of epsilon as a small positive number. So I look epsilon to the right of a, epsilon to the left of a, and I make a little gate. These are my parentheses there. And I ask myself, will it ever be the case that the terms of my sequence become trapped within the epsilon gate? And so I start looking at my sequence. A1, well, no, A1 is not within the epsilon gate. A2, A3, no, no, no. But eventually, there becomes a point where my subscript, we call it capital N or big N, I have a big N subscript where that sequence term gets within my epsilon gate. And not only does it get within the gate, but all the terms from then on out are trapped within epsilon of A. If that happens, then the sequence converges to A. Now, I need to be a little bit careful. It can't just happen for one epsilon. Maybe after that, I say, oh yeah, I picked an epsilon, and I found a big N, so that all my terms after the big N were trapped within epsilon. Then I pick a smaller epsilon. And I ask, I sort of play the game again. Is there some other big N, so that after some point, all the terms of my sequence are trapped within that smaller epsilon of A. And if that's true, then I make an even smaller epsilon, and on and on and on. Basically, I want to know that for any epsilon that I pick, for any epsilon gate around A, is there some term of the sequence that eventually enters into that gate, and it never escapes? The terms of the sequence never escape after that point? And if that happens, if that's so, then that's exactly what it means for the sequence to converge to A. Here it is in more official language. A sequence, the sequence of A sub n, converges to a real number A, if, for every positive number epsilon, there exists a big N, that's a natural number, and I think big N will be a subscript of A. There exists a big N such that whenever N is greater than or equal to big N, it follows that the absolute value of A sub n minus A is less than epsilon. I usually read this by saying that A sub n is within epsilon of A. Right, see if you understand that. A sub n is within epsilon of A. My A sub n's are all inside the epsilon gate. Or you might read this as using the word distance. The distance between A sub n and A is less than epsilon. There are a few ways that we indicate convergence of a sequence. The arrow is common, I like this. The sequence A sub n converges to A, or I can use the word limit. The limit of A sub n equals A. Or I can say the limit as n goes to infinity of A sub n equals A. We'll often talk about the epsilon neighborhood of the number A. So again, I kind of have this number A, and I think, well, let's look epsilon to the right of A and epsilon to the left of A, and all the x values within that region. It's just a set. It's the set of all x such that x is within epsilon of A. The idea of convergence is that we say that the sequence converges to A if the terms of the sequence sort of end up in that epsilon neighborhood, no matter how small we make epsilon. Right? For any epsilon, I can make an epsilon neighborhood, and eventually all the terms, all the ending terms of my sequence end up in that epsilon neighborhood. One more way of thinking about this definition. Here's a concise way of expressing convergence. The sequence A sub n converges to A. Another way of saying that is, for all epsilon greater than 0, there exists a natural number big N such that n greater than or equal to big N implies A sub n is within epsilon of A. For all epsilon greater than 0, there exists big N, a natural number, such that n greater than or equal to big N implies A sub n is within epsilon of A. This is kind of cool because it looks like a horrible mashup of symbols, and you can write this down for one of your friends and really impress them. But it's also kind of a good way for you to practice the definition of convergence. 2 or 3 times a day until it's memorized. Write this down, look at it, and think about it. Write down the picture, look at the picture, and think about the picture. Memorize this. It will help you understand it. The more you understand it, the more readily you can remember it. All right, it's back and forth. Go back and forth between the memorizing and the understanding. All right, let's do an example where we use this definition of convergence. I have the terms of my sequence are defined. A sub n is n over n plus 1. Let's prove that this sequence converges to the number 1. A lot of these convergence proofs have sort of a pre-proof to them. And I'll just kind of show you what I mean. What I'm after is that given epsilon greater than 0, we want an index, we want a subscript, little n, large enough so that the difference between A sub n and 1 is less than epsilon, right? So that my A sub n term is within epsilon of 1. And so this is what I want. I want eventually to show that this absolute value, A sub n minus 1, is less than epsilon. Well, let's just simplify this a little bit. And it's a forward implication, which is a little bit weird. I'm kind of going backwards because this is what I want to conclude. I don't want to start off with this. But let's just go with this and see where we end up. Another way of saying that is replace the A sub n with what it really is. It's n over n plus 1. Simplify the stuff in parentheses. Okay. And then actually apply the absolute value at this point. That implies that 1 over n plus 1 is less than epsilon. And let's solve for the n. Let's try to get the n by itself on one side. So this turns out now that I can take the reciprocal of both sides and get n plus 1 is greater than 1 over epsilon. And then I get n by itself. And this is a nice place to be. Ultimately, I didn't say it before, but this is kind of where I wanted. I wanted to end up with n by itself on one side of the inequality. This is often our goal when we do this pre-proof work. Get n by itself on one side of the inequality. But at this point, it kind of tells me that's really where I want to start, right? I'd like to say that if little n is bigger than 1 over epsilon minus 1, then the nth term of the sequence is within epsilon of 1. But all my implications have actually gone in the wrong direction. At this point, though, I realize, wait a second, all of these implications are actually reversible. And you should take some time and guarantee that they really are. So let's start at where we ended up, and let's trace it backwards. If little n is greater than 1 over epsilon minus 1, then n plus 1 is greater than 1 over epsilon. That implies 1 over n plus 1 is less than epsilon. That implies this statement with absolute value. That implies this other statement, which implies a sub n minus 1 in absolute value is less than epsilon. That's actually what we wanted. And so this pre-proof part often works backwards. We start with our conclusion, and we end up with a nice expression involving only n on one side, and then we realize that I could have done this in reverse also. So this conditional, this if-then statement, this is the important part. So I'm going to label this with a star and use that statement in my real proof. Okay, so here we go with the real proof now of the example. So in my pre-proof, I found the if-then. So, and I'm also putting the definition of convergence up there just for handy reference. Proof. Let epsilon greater than 0 be given. This is will almost always be your first line of a proof. Choose big N, a natural number, such that big N is greater than 1 over epsilon minus 1. Now, if you didn't know the pre-proof, you would look at this 1 over epsilon minus 1 and think, what? Where in the world did they get that from? It looked like it was just pulled out of thin air. But there's a reason for it. We'll see why that is the right number to choose. Okay. Let n be a natural number, and observe. If n is greater than or equal to big N, then n is greater than 1 over epsilon minus 1 because of how my big N was chosen. Oh, and totally, by the way, how do I know that I can choose a big N that's bigger than this number? It's because of the Archimedean property number 1. Okay, so I'm at the point where if n is greater than or equal to big N, then n is greater than 1 over epsilon minus 1. But now I pull the star that I found in my pre-proof. By the star statement, that implies that the absolute value, a sub n minus 1, is less than epsilon. And that's exactly what we needed to show. I needed to show that a sub n is within epsilon of 1. Could we have chosen big N greater than 1 over epsilon? I had big N was greater than 1 over epsilon minus 1. Yes, I can. There's no danger in choosing something bigger, right? I can say, instead of let's choose n bigger than 1 over epsilon minus 1, I could have said let's choose n bigger than 1 over epsilon, plus 1,000. That would have been good. As long as I take something bigger than the 1 over epsilon minus 1, I'm good. Here's another example. In this case, the terms of our sequence are defined. A sub n is 3 cosine n over n. Let's prove that this sequence has a limit of 0. It converges to 0. And maybe you can see that this ought to make sense anyway. The n in the denominator gets bigger and bigger and bigger, whereas in the numerator, cosine n always bounces back and forth somewhere between -1 and +1. So the numerator is somewhere always between -3 and +3. The numerator is bounded, the denominator is unbounded. It seems reasonable that this sequence converges to 0. Let's prove it though. So here's part of my pre-proof. I'm looking where I want to end up. In the end, I want the nth term of my sequence, minus 0, to be less than epsilon. I want the nth term of my sequence to be within epsilon of 0. And I'll start writing my implications if and only if. Just try so I can remember that eventually I'll be working backwards. Well, I can simplify that absolute value a little bit. We get 3 absolute cosine n over n is less than epsilon. And that's if and only if n is greater than 3 absolute cosine n over epsilon. So this is pretty good. Remember, my goal is to get n by itself on one side of the inequality. But there's a problem. I also still have an n on the right side. But here's where I can use the fact that cosine n is always between -1 and +1. And so in absolute value is always between 0 and 1. So I'm allowed to replace this guy that I've just boxed. I'm allowed to replace that with something as big or bigger. And I can replace it with something at least as big. What if I replace that cosine of n, the absolute value of cosine n, with just 1? Now, I lose my bidirectional implication, but that's okay, because what I really want ultimately is n by itself on one side of the equation and an implication that works from right to left. So let's work it backwards. Let's just make sure this is right. If n is greater than 3 over epsilon, then surely n is greater than 3 over epsilon times the absolute value of cosine n, which at its biggest is 1 and its lowest is 0. And then I can work backwards, and I get to my original statement that shows the difference between the term value and the limit value. All right, so just a little highlight. It's important to recognize when our implications are bidirectional and when they only work in one direction. Thus, all right, so kind of encapsulating this, what I've just found, if n is greater than 3 over epsilon, then 3 cosine n over n is within epsilon of 0. Now for the actual proof. Let epsilon greater than 0 be given. Choose big N, a natural number, such that big N is greater than 3 over epsilon. Okay, it's a mysterious number if you didn't look at the pre-proof, but now we'll see why that works. Let n be a natural number. If n is greater than big N, if n is greater than or equal to big N, then n is greater than 3 over epsilon. That comes from the fact right over there. But now I can use the star statement, because I know something about if n is greater than 3 over epsilon. By star, this implies that the nth term of my sequence is within epsilon of 0, as needed. Thus, that sequence converges to 0. Divergence. A sequence that does not converge is said to diverge. And there are two ways that a sequence can diverge. In this first example, the terms of the sequence just go higher and higher and higher. They diverge to infinity. In the second sequence, -1/2, 1/2, -1/2, 1/2, -1/2, 1/2, the terms just bounce around. They never actually get arbitrarily close to some number. How does the definition of convergence fail for these? Well, maybe I'll look at the second one. Maybe I can imagine my term -1/2, and there's a positive term 1/2. And if I pick any number, I don't know, let's just say 0, but you can choose any number, you can form an epsilon around that number, sort of an epsilon neighborhood, an epsilon gate around that number, so that the terms of the sequence never get within that that epsilon gate. So the sequence never converges to 0. But actually, now you're asking yourself, what if I actually chose, say, 1/2 as my point of convergence? Can the sequence actually converge to 1/2? So let's make our epsilon neighborhood around 1/2. What happens? The terms of the sequence, -1/2, 1/2, -1/2, 1/2. You know what? There are infinitely many terms within epsilon of 1/2, since they keep bouncing back and forth and back and forth. No matter how small you make epsilon, even if epsilon is tiny, it still contains infinitely many terms. But the problem is that there's no point after which all the terms of the sequence are within epsilon of 1/2. I'm always going to be having some terms that bounce out of that epsilon neighborhood. All right, our last point is uniqueness, and this is an example of how we might use the definition of convergence within the proof of a theorem, the proof of a fact. So the fact here is the limit of a sequence, when it exists, is unique. Here's a proof. Suppose, for contradiction, that my sequence a sub n converges to L, and that same sequence converges to M, and that L is not M. So I might draw a little picture here about what I mean. I have a number L, I have a number m, and I'm imagining that somehow in some crazy world, the terms of my sequence get arbitrarily close to L after some point, and they get arbitrarily close to M after some point in my sequence. Let epsilon be 1/3 that distance between L and M. So in the picture here, I'll divide that little segment into thirds, and so epsilon is 1/3 of the distance between L and M. And what I'll do is I'll actually continue that 1/3 on the left of L and to the right of M, and that's actually making my epsilon neighborhood of L and my epsilon neighborhood of M. Now, by definition of convergence, there exists a big N1 such that n greater than or equal to n1 implies that the nth term of my sequence is within epsilon of L. So after some point in the sequence, all the terms of the sequence are within epsilon of L. Similarly, there exists some big N2, so that if little n is greater than or equal to big N2, then the nth term of my sequence is within epsilon of M. Oh, well, that seems to indicate that all of those terms would be within M, within epsilon of M. I mean, from the picture, right, it seems obvious that this can't happen. One more idea here. Let big N without a subscript, let that be the maximum of N1 and N2. Now, let's choose a little subscript N naught. So choose a subscript N naught that is legitimately as big, at least as big as that big N. So what do I know about that N naught? Well, A sub N naught is within epsilon of L, so A sub N naught is here. And A sub N naught is within epsilon of M. A sub N naught is here. Okay. Clearly this is ridiculous, but really what makes it ridiculous is the triangle inequality. So I'm going to finish the proof by using the triangle inequality to show that there's a contradiction. 3 epsilon happens to equal the absolute value of L minus M. And let's break this up. I do a little trick. I'm going to subtract A sub N naught and add A sub N naught. And so that's the same equality. But now I'm going to use the triangle inequality because triangle inequality A plus B, absolute value is less than or equal to absolute value of A plus absolute value of B, where L minus A sub N naught is my A sub N naught minus M, that's my B. And so this is less than or equal to absolute value L minus A sub N naught plus absolute value M minus A sub N naught. And since it's in absolute values, it's okay for me to switch the order of those two terms. But now look at this. That first absolute value, that's less than or equal to epsilon. That second absolute value, that's less than or equal to epsilon. So I add the two epsilons together, I get 2 epsilon. Wait a second, this is ridiculous. Look at the beginning and the end of this inequality. 3 epsilon is less than or equal to 2 epsilon. No, cannot happen, because epsilon is greater than 0. So with epsilon greater than 0, it is impossible to have 3 epsilon less than or equal to 2 epsilon. There's the contradiction, and that proves the theorem. The limit of a sequence, when it exists, is unique. All right, there's a lot here, 2.1 and 2.2. But let me emphasize again, the most important thing that you can do is understand convergence. It is foundational for the rest of the course. Memorize that definition of convergence and go back through our examples and see how we used that definition to prove convergence. Okay, I will stop there.